Okay, so hello everyone. So it's my great pleasure to introduce Farshid Shoushtarian for today's seminar. Farshid has joined ENST as a PhD student in 2017. His research focuses on developing decision support systems for agricultural water resources management, including reusable water at regional and watershed scales under future climate and demand growth scenarios. To do that, he has been utilizing agent-based modeling techniques and hydrological modeling methods to study the complex and adaptive system of agricultural water reuse in the Mid-Atlantic and the Southwest, considering the coupled human water systems. He has published one peer-reviewed article. He has another one under review currently, and two in preparation, ready to be submitted by the end of this semester. So today he's going to present some interesting results from his PhD research. So without any further delay, let's welcome Farshid together.
All right. Thank you, Dr. Nagahwanazar. Good afternoon, everybody. My name is Farshid Shoushtarian. I'm so happy to present my exit seminar for you today. Before I start my presentation, I would like to apologize in advance if my voice is not clear and loud enough because I've been sick. I haven't recovered yet fully. So I would like to start by introducing my committee members. I've had the honor to have Dr. Masood Nagahwanazar as my advisor, Dr. Shir Mohammadi and Felton from ENST, Dr. Baker from Civil Engineering Department, and Dr. Andrew Crooks from the Department of Geography at University at Buffalo. So the title of my presentation is Sustainable Water Resources Management through Agricultural Water Reuse, Application of a Decision Support System. All right, about the outline. So my dissertation includes 5 chapters. However, due to time limitations, I'm not going to cover all of them. So I will start with a brief background and objectives of my dissertation. Then I will briefly cover 3 chapters of my dissertation, and I will finish with conclusions. So as we know, climate change, demand growth, and population dynamics have resulted in decreasing our access to safe freshwater resources. This means less available water for drinking water, sanitization, agriculture, food production, industry, and our environment. So the solutions to address the water crisis can be generally categorized into 2 major categories. We can decrease our water demand through conservation methods and increase our water supply through methods such as seawater desalination, rainwater harvesting, water transfer, and water reuse. Water reuse here means recycling treated effluent from wastewater treatment plants and applying it for different applications. Applications of water reuse can be categorized into 6 categories. We can use the recycled water in cities, for industry, for impoundment, in environment, for recharging groundwater, and in agriculture. As you can see in the top picture, a high percentage of our freshwater withdrawals are consumed in agriculture. On average, more than 70% of the freshwater withdrawal in the world is consumed in agriculture. And as you can see, there are just some countries in the world that use agricultural water reuse in the world. Therefore, agricultural water reuse has great potential in order to decrease the amount of water that is consumed in agriculture. We can decrease the amount of freshwater withdrawn for agriculture and using the recycled water. That's why the topic of my dissertation is about agricultural water reuse. So agricultural water use has several benefits, such as sustainable development, water conservation, increasing the water supply, decreasing the pollution that is discharged to our water bodies. However, it has its challenges. The challenges can be categorized into different categories, such as technical issues, social concerns, health concerns, environmental concerns, legal and economic challenges. These challenges add to the complexities inherent in water resources management and make it so hard and challenging for water resource managers and decision makers in order to manage water resources. And they have to consider multiple aspects, multiple criteria and objectives when they want to deal with agricultural water use projects. One of the solutions that is suggested by the scientific community in order to help water resources decision makers is using decision support systems. Decision support systems are able to simultaneously evaluate and analyze multiple criteria and objectives. Therefore, water resources managers and decision makers can use these decision makers beneficially in order to make better informed decisions and sustainably manage and plan agricultural water use projects. However, there are some knowledge gaps among the existing decision support systems. Knowledge gaps are about the gaps and differences existing in the existing codes of agricultural water use practices. We don't know about the dynamics of how farmers would adopt agricultural water use projects and their impacts on local water resources. We also don't know how to plan and manage agricultural water use practices sustainably, and we don't know their potentials in order to increase the sustainability of our water resources at watershed scale. Therefore, in order to address those gaps, the main research question of my dissertation was to capture the complex and adaptive dynamics of socio-hydrological systems inherent in sustainable water resources management when alternative water sources are introduced at the watershed scale. In order to answer this question, two objectives was defined. The first one was to investigate the dynamics of introducing an alternative water source into the portfolio of water supply. And the second one was to simulate the complete feedback loop between the decision of farmers, decision of policymakers, and the water resources in a coupled socio-hydrological system at watershed scale. Therefore, the decision support system that I've been developing include three main sections. The first section deals with the water quality aspects of agricultural water use projects. For these, I identified, collected, and thoroughly analyzed existing agricultural water use regulation and guidelines regarding any requirements and restrictions about the quality of recycled water. The two next sections deal with the water quantity of agricultural water use projects. More specifically, in the second one, I used bottom-up approaches in order to investigate the micro-scale dynamics of agricultural water use adoption by farmers and its impacts on local water resources in order to find best micro-level management strategies to manage and plan agricultural water use projects. For this third part, I switched gears into holistic views and used top-down approaches to investigate macro-scale dynamics of agricultural water use projects and their potentials in increasing sustainability of our water resources in order to find best macro-level management strategies to manage and plan these projects. In order to apply this decision support system, I chose two case studies in two completely different areas: Southwest in California in Southwest, and Maryland in Mid-Atlantic. As we know, Southwest is the hottest and driest region in the US. Precipitation in this area has been fluctuating. Temperature projections have shown that temperature is going to be significantly higher in this area, and aquifers in this area have been experiencing declining groundwater tables for the past 50 years. On the other hand, as we know here, we have hot and humid summers and cold winters. Precipitation data here shows that we have year-round precipitation, and recently we have been seeing massive events and changes in rainfall pattern. And temperature data shows that temperature in this area is going to rise, and aquifers in the Mid-Atlantic area have been experiencing with declining water table, saltwater intrusion, and low water quality. in this area, we are dealing with surface water quality issues too. All right, let's go to the first study. So in this study, I did a critical review on the agricultural water use regulation and guidelines in the world. First, I use various keywords and Google Scholar search engine in order to identify my case studies, which included countries, international and national organizations, and state agencies that issued any sort of regulation or guideline regarding recycled water quality. Out of the 83 cases that I collected, 70 of them were suitable for this study. As you can see, they were distributed all around the world, from states in Canada and United States to European countries, in countries in Africa, Middle East, Asia, and Australia. So let's go to the US. Unfortunately, we don't have any federal regulation or guideline regarding agricultural water use in the United States. In contrast to drinking water, it is up to states to come up with their regulation or guideline for agricultural water use. As you can see in this figure, those yellow states, they have regulation or guideline for food crop and non-food crop practices. Those orange states have regulation or guideline for just non-food crops. Arkansas, the blue one, have regulation or guideline for food crop, and those red states don't have any regulation or guideline. Even in those states that have any regulation or guideline, we have seen a lot of gaps and discrepancies, which I'm going to briefly talk about. So let's look at the Maryland, as we are in Maryland, as an example. So we have 4 classes of recycled water here. For irrigation, 3 classes are allowed. They categorize the classes into restricted public access and unrestricted public access. And class 3 is allowed for using in unrestricted public access, and class 1 and 2 for restricted public access. In general, those regulation and guidelines for unrestricted public access and for food crops were more stringent than the other ones, and which makes sense. They want to protect the human health. So in order to thoroughly analyze those regulation and guidelines regarding recycled water quality, I classified those parameters into 3 major parameters: human health parameters, agronomic parameters, and physicochemical parameters. And under all of those parameters, I compared them and compared the restrictions with the scientific knowledge that we have in order to critically review them. As I don't have much time, I'm just going to quickly cover pathogens and nutrients here. However, if you are interested, I would recommend you to read our publication, which was published in the year 2020 in the Journal of Water. So in total, out of the 70 cases that I studied, pathogens was the parameter that was mostly used by those regulation and guidelines. The second one was TSS, and the third one was BOD5. As you can see, there are a lot of regulation and guidelines that do not cover a lot of these parameters. Let's look at the pathogens. As we know, pathogens is one of the most important parameters regarding recycled water quality. They can be detrimental to humans that directly consume products irrigated with recycled water. They can be detrimental to workers in farms and workers that work in the supply chain industry, and even they can be detrimental to those who live in the vicinity of farms that are irrigated with recycled water, especially with sprinkle irrigation. Those regulation and guidelines that required any pathogens restrictions for agricultural water use could be categorized into 2 categories. However, under those categories, we saw a lot of gaps and discrepancies among those regulation and guidelines. Here, for example, as you can see, under the restrictive one, for example, Arizona and Florida require no zero concentration of microbial concentration, comparing to Kansas, Texas, and Delaware, which require about 1.5 of microbial concentration. This figure shows on the x-axis shows the name of those entities that issued those regulation and guidelines, and the y-axis shows the microbial concentration in the log unit. The other parameter of importance is nutrients. We all know that nutrients are very important for agriculture. However, high concentration of nutrients can be detrimental to agriculture. High concentration of nutrients can, for example, overstimulate crop growth and can result in eutrophication in water bodies. For example, here, unfortunately, you can see that zinc and boron were the two parameters that were mostly used by those regulation and guidelines, and by just only 15 out of the 7 that I studied. The other important note is treatment levels that were required on those regulation and guidelines. In general, we have 4 treatment levels in wastewater treatment plants. The first one is primary, then it goes to secondary, then it goes to tertiary or advanced, and then it goes to disinfection. As it goes on, the recycled water quality gets better. However, as you can see, this figure shows those treatment levels and the number of regulations that require them in their regulation guideline. You can see secondary treatment where the level that was required by most of them, and primary was required by least of them. And there were a lot of regulation and guidelines that didn't require any treatment levels for agricultural water use practices. In general, in summary, we concluded that the rationale behind issuing or establishing those regulation and guidelines were not clear. Those regulation and guidelines were mainly human-centered. They were insufficient regarding some of the most important parameters like pathogens, heavy metals, chemicals of emerging concerns, and nutrients. Even those that had any that included those parameters, we saw a lot of discrepancies among them. Regarding the treatment levels, they were just included in some of the regulation and guidelines, and even in those that included, we saw a lot of discrepancies. Those discrepancies were could be due to differences about approaches to public health, different levels of education, development or economic status, and different climatic, geographical, and environmental conditions. In general, those discrepancies as gaps are one of the main barriers of implementing agricultural water use projects. Now, let's go to the second study. In this study, I investigated the micro-level dynamics of agricultural water use systems using an agent-based model. So, the case study here was an irrigation district called the Water District. It is located in California in the west side of San Joaquin Valley. This irrigation district provides irrigation water to 45 acres of farmland in this area. And currently, the only source of water here is provided through a contract with USBR in order to provide almost 140,000 acre-feet per year of water from the Central Valley Project. However, due to drought conditions in California and delta pumping restrictions in the area, the CVP allocations haven't been reliable, and they shown that they had decreasing trends since 1990 to 2013. Therefore, due to the shortages in CVP deliveries and the fact that there is no secure alternative water in this area, farmers and the district have been experiencing with economic hardship, which resulted in increasing fouling practices in this area. Therefore, in order to address this challenge, they started an agricultural water use project called North Valley Regional Recycled Water Program. They wanted to introduce a new source of water for these agricultural areas. This project included 2 cities of Modesto and Turlock, and they wanted to transfer the recycled water from the wastewater treatment plants in those cities to this irrigation district. Water supply demand and projections show that they are going to need to provide between 40,000 to 60,000 acre feet per year of water for this irrigation district through this project. So they plan for some expansion plans in order to expand those wastewater treatment plants to keep up with the demand. This figure shows the years in the x-axis and recycled water supply capacity in the y-axis. And in those lines, you can see how they want to expand those wastewater treatment plants. However, it's not that easy. As I mentioned, agricultural water reuse projects have a lot of challenges. One of the most important one is the social one. We don't know how the farmers in this area would adopt this agricultural water reuse project. There have been a lot of agricultural water reuse projects that, due to public opposition, they had to shut down the projects entirely or change the plan entirely in order to make farmers adopt that projects. So in order to study this project, I use agent-based modeling to see how farmers would adopt this project and how it affects local water resources. First, I would like to introduce agent-based modeling to you. So agent-based modeling is a computational method for simulating complex systems. It is a bottom-up approach. It is an artificial intelligence method categorized under the embodied intelligence. In general, we use micro-scale data from physical environment and built environment in order to develop an artificial world. Then we simulate the model and we come up with data, and we end up with some data. And from that data, we conclude some conclusions, and we do simulations, sensitivity analysis, and scenario analysis. Agent-based models also let us to model different entities and the interactions between them using the environment that they are located at. Agent-based models have three major components. First is the agents, the second, environment, and the third is the interaction between them. Agents can be any entities, not just humans. This is just for illustration. They can be from countries, institutions, people, bees, mosquitoes, deers, anything until to viruses even. So we develop some algorithms for those agents, and we let them interact with each other, and we see the emergent phenomena that comes out of them. So benefits of agent-based modeling includes capturing the emergent phenomena. They let us to include stochastic processes. They let us to include geographical and social sciences in our models. And we can, using agent-based models, we can develop agents that are autonomous, heterogeneous, adaptive, and have unlimited number of parameters, rules, and memory. Agent-based modeling have been used in studies of virus spread, evacuation studies, for studies of flocking birds, studies of traffic, and in water resources, the applications started from 1995 till now. It's a growing field, especially under the human water systems field. So about the agent-based model that I developed. First, I propose a framework of, it was a social hydrological framework in order to incorporate social and hydrological aspects of this project. The model included two types of agents. The first type was almond farmers. I chose almond because almond is the major crop grown in this area. It needs a lot of water throughout the year, and it's a very expensive crop. So, as the model ran daily, almond farmers did a water resource mass balance every day using effective precipitation, CVP allocations, and the amount of water that their almond trees needed. when they determine if they have water shortage, they had the opportunity to use alternative water sources, including groundwater, transferred water, and recycled water. They could use recycled water after adopting the agricultural water use project. The adoption was simulated using a submodel. The submodel used a psychological theory called theory of plant behavior, which used survey data from the study area, network analysis, and financial analysis. So the model ran daily. Farmers do this every day. And at the end of the day, they would sell their crops, earn profits, and earn money in order to be able to pay for irrigation system, operation systems, maintenances, and for buying those recycled water or transferred water. The other kind of agents, wastewater treatment plants, we have two treatment plants here. Their major task was to provide recycled water to farmers. They would transfer the recycled water to their storage tanks, and then from the tanks to the farmers who adopted the recycled water and who could pay for it. And they would prioritize those farmers based on their distance. So the higher the distance, the lower the priority. And I developed this agent-based model using NetLogo and Python. Doesn't work. Okay, so the environment of the model was modeled in a stylized way. So the agent, the almond agent, the almond farmers were stochastically located at the model based on their area. They were the area was categorized into three areas: northern, central, and southern areas. So after the model was developed and verified, so that we know that the model was working fine, we did a sensitivity analysis. More specifically, I used design of experiment in order to do this. Results showed that unit price of recycled water and groundwater availability were the most important parameters that affected the total recycled water consumption by farmers. The third parameter that was important was the interaction between the production rate of the Turlock wastewater treatment plant and the unit price of CVP water. After that, I designed 4 scenarios in order to explore how this agricultural water use project would do under various scenarios. Scenarios included normal, moderate drought, severe drought, and wet conditions. So let's look at some of the results. So in this figure, you can see the years in the x-axis, the years of simulation, 84 years of simulation. And in y-axis, you can see the farmers' total water shortage. As you can see under all of the scenarios, due to the agricultural water use project, farmers' total water shortage were significantly decreased, especially under scenario 3, which was the severe drought condition, which decreased farmers' water shortage by 60%. Moreover, the results showed that farmers' total groundwater consumption were decreased in all of the scenarios that it was available to farmers. For example, under scenario 4, which was the wet conditions, the farmers' total groundwater consumption was decreased by 75%. Results, this figure shows the years of simulations in x-axis, and y-axis shows the number of farmers that adopted those agricultural water use project. These trends showed results in accordance with a theory called diffusion of innovations, which allowed us to qualitatively validate our model. This theory of diffusion of innovation is a theory in order to investigate the diffusion of new ideas and technologies in new populations. In summary, we concluded that agent-based modeling can be beneficially used to get valuable insight into the complex and adaptive dynamics of agricultural water use projects and their impacts on local water resources. This agricultural water reuse was able to successfully decrease farmers' total water shortage and groundwater and transfer water consumption. Agricultural water use adoption is a gradual and time-consuming process, which can be affected with various parameters, for example, like socioeconomic parameters. Decision makers have to pay special attention to these parameters in order to identify them and manage them. For example, in this study, we found that the unit price of recycled water is the most important parameter. So the decision makers of this project have to pay special attention into setting the price for recycled water in this project. Now let's go to the third study. So in this study, I investigated sustainable water resource management through agricultural water use in Maryland. You may ask, why water use in Maryland? So as we know, groundwater is the primary source of water in Maryland, and agricultural and urban water consumption has been increasing in this area. As a result, we have been experiencing extensive groundwater level decline in this area. In this figure, you can see that the major portion of the water that was consumed for irrigation in Maryland coastal plain came from groundwater sources. And this figure shows the level of groundwater in 4 monitoring wells in the Maryland coastal plains. You can see how the groundwater level has declined since about 1980 till 2018. So the case study of my study was located at the Choptank River watershed. It is a major agricultural watershed. More specifically, the case study was located in Talbot County, agricultural areas around the Easton wastewater treatment plant. This area was also identified as a suitable area in order to implement agricultural water reuse by one of my former lab mates, Malachi Paul, using geospatial multi-criteria data decision analysis. About the Easton wastewater treatment plant, it is one of the major treatment plants in Maryland. We just started its service since 1914 and has received a lot of funds in order to expand and enhance its operations. Therefore, I use the same framework in order to study this case study. However, due to completely different conditions, I have to develop a completely different model in order to study this one. So I use NetLogo and Python in order to develop this model. In this area, corn farms are the major farms in this area. So the agents in my model included 166 corn farms in the 15-kilometer radius of the treatment plant. According to Maryland Extension Services and NRCS, corn farms in this area need irrigation in 4 months, including June, July, August, and September. Therefore, as the model ran daily, farmers would determine their daily irrigation demand using the formula that you can see in this slide. These numbers that is provided in the table could be multiplied by a number between 0 and 2.6 due to weather conditions, because they are based on long-term historical data. Under different climate change scenarios, they would be multiplied by different numbers. So in this area, the primary source was groundwater. So the corn farmers use groundwater as the primary water source. If it wasn't enough for them, they would use surface water. After introducing recycled water into the area, they could use the recycled water. However, after adopting it and if they could pay for it. So the model ran daily. The farmer do it for every day until the end of the year. At the end of the year, they would sell their corns, pay and earn profits, and make money in order to be able to pay for their operations, maintenance of their irrigation system, and be able to pay for costs of irrigations. One important thing here was I wanted to look at the sustainability of a farmer's water supply. So I used the well-known sustainability index introduced by Professor Lutz. These index include 5 criteria. The first criteria is reliability. It was defined as the probability of meeting the demand by the supply. And it was calculated based on time and based on the volume that was supplied by the supply. The other one was resiliency, that was defined as the probability of the water supply system recovery from any stress. The other one was the vulnerability of the water supply, which was defined as the potential value of water deficits. And the maximum deficit, which was defined as the worst case annual water deficit. After the model was developed, I needed to verify the model in order to check whether it behaved as it was designed. So I did this using 3 methods of code testing, expected outcome alignment, and extreme test. Then I did time varying uncertainty analysis and sensitivity analysis using Monte Carlo simulations and moment independent sensitive analysis using the SALIP library in Python. After that, I used the macro level results of diffusion of innovation theory in order to qualitatively validate my model. After the model was validated, 4 scenarios based on climate change that was introduced by IPCC was used in order to explore this agricultural water use project. As you can see, scenario 1 was simulated under the business as usual, scenario 2 under RCP 2.6, scenario 3 under RCP 4.5, and scenario 4 under RCP 8.5. After scenario analysis, I use reinforcement learning as a machine learning method in order to create an artificially intelligent manager agent to manage and plan this project. And the idea was to learn and get insight from this artificially intelligent agent. So the agent was able to change 2 most important parameters that were identified in the sensitivity analysis of the model. The whole idea about reinforcement learning is about an agent which does some actions in an environment based on states that it is in, and it gets a reward. After a time, it tries to enhance its actions in order to maximize its reward. That is the basic about reinforcement learning. So in order to do the multi-objective optimization, I use the scalarization method in order to include 5 opposing objectives into 1 reward function. As you can see, the objectives of the artificially intelligent manager agent were to maximize farmers' water supply sustainability, number of recycled water users, unit price of recycled water, and to minimize farmers' groundwater consumption and the wastewater treatment plant storage capacity. In brief, the results of sensitivity analysis, you can see here in this figure, the x-axis shows the simulation years, and the y-axis shows the delta, which is the index in order to show the importance of parameters. And this is for groundwater consumption as the response variable. This shows that the method that we use, we're able to capture the complexities in agent-based models. And it shows that unit price of recycled water and temperature were among the 2 most important parameters in different years that affected farmers' groundwater consumption. Results of the model under various scenarios showed that the agricultural water use was able to decrease the amount of groundwater consumption by farmers. For example, here under the business as usual scenario, you can see that farmers' total groundwater consumption were significantly decreased almost by 4 million cubic meter per year after the first 15 years. Results of the multi-objective simulation-based optimization showed that the manager agent was able to adaptively change its decisions in order to maximize its reward. The top figures shows those 2 parameters that the manager agent was able to change and in order to maximize its reward, which is shown in the lower figure. under all of the scenarios, these results are for business as usual, but under all of the scenarios, the agent was able to maximize its rewards in order to sustainably manage or plan this agricultural water reuse. And the idea was to learn how it changes its decisions based on different situations and different times in different months. So in conclusion, we concluded that this time-varying sensitivity analysis method that we use for sensitivity analysis of the agent-based modeling was a proper method for, especially for complex adaptive systems, because it was able to capture the complexities inherent in them. Climate change, unit price of recycled water, and the wastewater treatment and storage capacity were identified as the most significant parameters affecting this project. This agricultural water use project could significantly decrease farmers' total water shortage, groundwater consumption, and surface water consumption. However, climate change effects decrease the positive effects of this project on the sustainability of water resources. About the farmers' water supply reliability, resiliency, and sustainability, these results showed that this project was able to significantly increase those criteria of farmers' water supply. And the artificial intelligence agent was able to adapt its decisions in order to reach its objectives in various scenarios and in different times. In total, in conclusion, we concluded that agricultural water reuse is one of the most important ways in order to address the water crisis in the world. Those gaps and discrepancies that we found in those regulation and guidelines are one of the most important barriers for implementing agricultural water use projects. Agricultural water adoption is a gradual and time-consuming process, which can be affected with various parameters, and decision makers have to pay special attention in order to identify them and manage them. Agent-based modeling was identified as a good method in order to capture the macro-scale complexities inherent in agricultural water use projects, and decision makers and water resource managers can beneficially use reinforcement learning in order to get valuable insight, which is supported by artificial intelligence in order to make better decisions to sustainably manage our water resources and agricultural water use projects. At the end, I would like to thank my committee members. Then I would like to thank everyone in ENST department. Then I would like to thank my funding agencies, Conserve, USDA, NIFA, and graduate school. And at last but not least, I would like to thank my wife, family, and friends. By that, thank you so much. These are some of the references.
Questions from the audience?
For your second study, you put up a series of figures, and it looked like scenario 3, I think, and each one of them was very distinct from the others. Can you remind me what scenario 3 was?
It was the severe drought. Yeah, which decreased the amount of groundwater and transferred water that was available to farmers. So they would, I mean, it affected the amount of money they had in order to be able to pay for buying recycled water. However, they were more willing to use recycled water. Sure.
We have a question online from former grad student Brian Scott.
Sure.
He says he's been touring California the last few weeks, and the reservoirs he's seen are dramatically depleted or empty. And it also appears that water resources are maybe being diverted away from large-scale restoration projects, particularly wetland restorations. He'd like to hear whether you think your work does or could consider impacts of water use optimization beyond strictly agricultural needs, such as wetland restoration type projects. Is there a way to kind of incorporate that into your modeling approach, do you think?
Well, you can, but for my study, as this is the first study, looking at the micro scale and macro scale of agricultural water use, I couldn't include all of the things in the science, but yeah, potentially, yeah, you can do this. You can do that in order to look how they would affect the amount of water that is available in wetlands, and especially under this SIGMA, the Sustainable Groundwater Management Act, that is going on in California. I think the situation is it's very complex in California. Unfortunately.
Yeah.
Sure.
Was there any sensitivity in the models and building these parameters to sort of the infrastructural cost to deliver water and maintain the systems? I mean, adoption on the part of the farmers assumes that magically water can get there, but it's traversing a lot of jurisdictions, and it's pipes and pumps and.
Yeah. So in the model, the only thing that was incorporated was the unit price of water that farmers had to pay for it. Those costs incorporated, those costs related to the infrastructure wasn't incorporated in the model. However, I know that, for example, in California, irrigation districts and water utilities get a lot of fundings from state agencies in order to do water reuse projects. And in Maryland, it is growing. State agencies, for example, Maryland Department of the Environment, they are exploring different aspects of water reuse. I worked on a water reuse for doing salt brine application during winter, and for agriculture, they are exploring different applications of water reuse, because we are trying to show that it is a proper method in order to address the groundwater level defines challenges here. But that's a very good question. I think that would be the next step. Somebody comes and add those complexities into the system so that we can see how it affect the decision makers would need to know those numbers. This is just the unit price of water. Yeah.
So I know your focus is on the application in agriculture, but you mentioned how there's, in the very beginning of your intro, that there's other potential applications such as an industry or urban. Do you think there's more, I guess, interest in using it in agriculture first, or it's comparatively to some of those others applications?
I would say it depends on the area. In California, Florida, and Texas, as far as I know, they are putting a lot of price into using water reuse for drinking water. However, there are growing numbers of projects to apply in agriculture. The social impact that I talked about, it's a very big problem, because the conserve center that I've been working in, we have been trying to let farmers know that they can safely use recycled water into their practices, because they are concerned about their crops, their business, their soil, and it is growing. It takes a lot of time, but hopefully we'll see a lot of projects here. So far, I couldn't include the video. I think most of you have seen that Dr. Azar shown here about a farmer in Maryland in the coastal plains in Kent County, I think, who had a lot of problems with groundwater. He couldn't, he didn't have access to the groundwater, started using recycled water, and his business started growing up again. So, but yeah, there are a lot of other applications and potentials. I was working with Maryland Department of Transportation with Dr. Nazar in order to use recycled water to produce salt brine instead of using fresh water, so that we could decrease the amount of fresh water used in those projects. I would see I think it takes a lot of time to use for drinking water here, but definitely in California, those states that have water shortage, like Arizona, California, Florida, they are pioneers. Israel, they are in Australia, they are the pioneers of water use.
I think we'll need to call off questions there. As a reminder that in the chat box, there is a link, and all the graduate students and faculty should have received an email with a link to an evaluation a few minutes ago. And so be sure to fill that out. Let's thank Farshid one more time for his great.
Thank you so much.